Good morning, kiddos. Or good afternoon, good evening. I don't know what time it is where you are. Either way, welcome to part 18 in my BUTTMAM series on the TMAM I've built in shapes.io. Today, I'd like to talk to you about the ADJ, or anti-jank device. I've referred to it a few times and, well, it's part of the factory, so let's talk about it. Now, before we dive in, I'd like to issue the following disclaimer that's kind of important. It doesn't actually work properly, which is quite ironic. Or maybe let me rephrase that. It does work as intended, but it doesn't contribute anything to the factory. At least, not anymore. So, let me tell you about the reason I built this anti-jank device. The very first idea behind it was to create a kind of machine that would output an error on the display if the TMAM was unable to find the correct shape. So it would search for a while, but I wanted to make sure that if you fed an outright impossible shape into the machine, it would detect that and indicate it at a given point instead of continuing the searching forever and ever. Because the thing is that this machine runs a trial and error based type of algorithm, right? And the cycler modules I've showed how they reset and start over whenever they reach the end. And this applies to all of the cyclers. The cyclers are pretty much identical to one another, so the looping mechanism extends to the entire algorithm. What that means is that when the last cycler uses up all of its candidates, then it will simply reset like the rest of them. In other words, if the TMAM has tried all possible candidates, it will simply be reset in its entirety and start the whole cycle over again. There is no piece of logic in the machine that tells it when it has exhausted all of its possibilities and has started over. Now, you might think, why not simply attach a trigger to the last cycler, and when that overflows, well, then that's the point in time where we've tried every combination and there's no point continuing, right? And the answer is, that's not accurate. Because of the lifeline, which I talked about last video, the sequential trial and error mechanism might kick off anywhere in the cycle. So there's no guarantee that a reset of the quad float cycler equals the end of the road. It might need to reset the algorithm, so it can try different combinations that were initially bypassed by the lifeline, if that makes sense. So the anti-jank device is basically just a glorified timer. That's all it is. When we input a shape, the clock starts, and if the machine doesn't find a solution within a given time, then it will indicate a fail. It's as simple as that. It's definitely not the most elegant solution, but it's the only one I could come up with. Now, apart from indicating when the machine has been unable to come up with a solution, the ADJ also performs a second function. After all, I called it the anti-jank device, and actually, it's a two-phased timer. After the first timer expires, the device will reset the wiring module and simultaneously start the second clock. And only if the second timer expires, then a fail will be indicated. The reason for the reset is because I noticed some janky behavior from time to time. Just to make absolutely sure, I issued this warning right here for whoever wanted to download this map. So there is some janky behavior from time to time. When, for example, you rapidly changed input shapes, the machine would sometimes not be able to find the correct solution and indicate a fail, even though the shape itself was perfectly doable by this machine. And, when trying out and testing, it turned out that sometimes when I removed the input altogether, waited for a few seconds, just to let the machine cool down or something, and then put the input back again, poof, it would suddenly just work. So that's what the ADJ does. First, it will allot the TMAM with a fixed amount of time to find a solution. If it can't, then the wiring will be reset entirely and it will try again. If the second time around it also fails, then the factory will be shut down completely and a fail will be indicated. Now, the reset operation that the ADJ performs is nothing more than suppressing a symptom. I'm aware of that. It doesn't tackle or solve the actual issue, and the issue must be located elsewhere in the machine. Some flawed logic or sloppy setup elsewhere in the wiring. And to be completely truthful, I haven't been able to pinpoint what or why exactly. But I have changed some wires here and there after having built the ADJ, and now it seems the reset function has become superfluous. The TMAM seems to have become slightly more robust and less prone to tilting. So, okay, having said this, I did say that I wanted to go over everything in this machine over the course of the series, and the anti-jank device is a part of that. So even though it has become kind of obsolete, it does feature some nice ideas, I think, wiring setups and mechanics that you might find, useful as inspiration, or at the very least, interesting to have a look at. And that's what we're gonna do. So, I'm gonna zoom out, and before we continue, I'm going to cut a few wires that will allow me to demo better. Okay, so here it is. This is the anti-jank device. It's just a long row, as you can see, connected to belt readers and filters, and it has two of these, pretty much identical loops. Okay, the point of departure for us is going to be the wiring. So let's go to where we need to go. This is where the input signal comes in. And I'm actually going to, now that I think of it, I'm going to shut it down. So, we have no actual input signal right here. Excuse me. The first thing that's going to happen is whenever we get a new shape, right? This timer, this is a 12-tick delay timer. It's going to interrupt the signal for 12 ticks, and then we can continue. So imagine we get a signal. I'm going to set up a constant signal right here. Why not take the blueprint shape? There we go. So this 12-tick timer, it interrupts the signal for 12 ticks. And then the first thing we're going to do is we're going to follow the line along right here. And here, it is going to send that shape into a constant sustained signal loop. Okay, so thanks to the XOR gate, this shape, this transistor will trigger. It will allow the shape to pass. And thanks to this OR gate and this transistor right here, that signal is sustained indefinitely. Okay? The signal is continued into this OR gate, and this OR gate is actually going to shut down the anti-jank device, but let's not look at that for now. So, we get this loop. You know what? I am making this up as we go. So the first thing I want to do is, let's see. Is it running now? Yes, it is running now. So as soon as we get a new shape, you see that these shapes start, creeping along the belt, right? This is the timer mechanism. So the first thing that's going to happen is for a brief period of time, the anti-jank device will be shut off. If this outputs a 1, then the anti-jank device will be shut down. It doesn't do anything. But this input signal, it runs through another timer. Okay? So this timed gate thing right here, its output here, it goes back, it runs through all of these transistors. I forgot the count, but I think it's like 40 or 50 of them. In the meantime, we have gotten this sustained loop of the signal, which has shut down the anti-jank device. Okay? But after, whatever length of delay this is, I believe it's 50 ticks, this comparing unit will output a 1, and thanks to this setup right here, it is going to shut off this signal, and this is going to turn on. It's going to enable this. It's going to kickstart this belt. So now we have a small timer running, which I enabled with the belt readers and this setup. I suggest you just have a look at this. So with the belt reader, that is how I set up the slow creeping movement of the anti-jank device, right? Of this belt right here. So the thing it's going to do is it's going to run this entire trajectory. It's going to come back, and this will be the end of the first timer. Okay, so I'm quickly going to fast forward to the point in time where that happens. Okay, here we go. So you see that these shapes have reached the end of the belt. I placed a trash can here, because I want to have a look at you. I don't know what's happening with me today. I want to have a look at the triggering system with you. What happens? Because this belt reader is going to trigger. It's going to trigger free flow motion. So right now, you see that these shapes have kind of like this creepy, creeping delayed kind of motion because of the belt readers. And as soon as this belt reader is triggered, that is going to enable all of the filters, and we're going to get free flow. Okay, so let's have a look at that first, and I'm going to place the next trash can right there. So as soon as this belt reader is hit, boom, there we go. Now this turns into free flow, and the next thing that's going to happen is that these shapes are going to make it around the bend. They are going to run through this storage unit, and they are going to trigger this belt reader. And this belt reader is kind of important because that's going to reset the entire wiring. Okay, so let's have a look at the wiring. You see that this belt reader is connected to this transistor right here, and that is going to do various things. First of all, it's going to emit a purple signal, which will move into the displays. We're going to have a look at the displays at a later stage. But if you ever notice like purple color on the display, this is where that comes from, right? So as soon as this is triggered, the thing that's going to happen is it's going to run into this comparing unit, and this comparing unit is another delay module, basically, right? So put the belt piece in. Come on. There we go. So now this belt reader is triggered, and because this is another delay module of, what is it, like 40 something ticks, right? It's going to briefly enable this XOR gate, which is going to shut down this signal. And now we're going to follow this signal down to see what it does. Down, down, down. Here, this signal is usually a 1, but now it's interrupted and it turned into a 0. And this delay module is an interesting setup, I think. I want to have a look at this with you in isolation. Because this is a pretty space-efficient delay module for, you know, the amount of delay you can set up with it. Let's see. Like I want to do this with a button. Come on. Where's my button? There. Forgot the hotkey. And then I'm going to connect the output with a display. Like so. So now, at this point, we have a one signal on the module. Now, let's see what happens when I press the button. It's going to trigger this delay. It's going to trigger this module, and when it reaches the end, it's going to reset itself, right? And it's going to change the output signal right here. So let's interrupt it. Now the signal is on again, and when I press the button, after quite a long delay, the display will be shut off again. Reset. Let's have a look at it again. The interesting thing about this type of delay module, and you know, I invite you to use it if you find any kind of benefit or purpose for it. The advantage of this is that it is exponential, right? So every, you know, piece, every, you know, XOR gate setup that you see right here that you add is going to double the delay time, right? So it's not linear, it's exponential. Right, so the way this works is that you, with the XOR gate, you're constantly going to, you know, make this XOR gate flicker because it receives a 1 from one side. It will therefore output a 1, and it's going to have a 1 tick delay to reach, you know, to feed back into itself, which is going to shut down the signal again. So you're going to get a 1 tick flicker on this one, and that delay is going to be doubled for each time you do this. Okay, so for each additional XOR gate module you attach to that, the delay time is going to be doubled. So I have 1, 2, 3, 4, 5, 6, 7, 8. And I don't know by heart what 2 to the 8th is because I suck at math. But anyway, that's how long this delay is. So final look at it, and you see it slowing down, right? The time it takes for this final module to trigger is delayed quite a lot. So I invite you to use this setup if you can use it. It's very useful for, you know, some purposes. In some cases, you can absolutely use this. So I'd say take a screenshot, have a look at it, how it works. Maybe you can optimize it. Probably there are more efficient ways to achieve the same thing with the wiring, but this is what my setup right here looks like. Okay, so delete, come on. We don't need you anymore, we don't need you anymore, and we're going to get back to the actual part in the machine. So, as I said, this signal is a 1 by default. But currently, we are simulating the interruption in the anti-jank device where the module is going to be reset. You know, and the interruption is sustained for this amount of delay right here. So, when this signal comes out, here a 1 is triggered. because that will, help with the resetting of the machine itself. But we need the actual 0 output for this time. And this runs to the right, where I don't really know what it does, but it has something to do with, I think it interrupts or it pauses the pulsing mechanism, right? And then it runs to the left, where it performs a slightly more important function. Here, this wire right here is connected to all of the cycling modules, right? All of the cyclers that we spoke about previously. And what it is going to do is it is going to shut down this transistor. It's going to cut the feed to this transistor. And I hope you remember from previous videos that this wire in the machine is what enables, disables, and resets the cycler modules. So that's exactly what the cutting of this signal, turning it from a 1 into a 0, is going to achieve. It's going to cut all of these wires of all of the cyclers, which will have the effect of resetting them back to their first candidate. That's what it is. Okay, so this interruption takes place, and I'm going to connect this wire again. So this interruption takes place. And now, well, remember this part. This is a timer, right? And I have interrupted the timer. So at the moment, we are cutting the signal, but after, 40-ish ticks, that interruption itself is stopped. So now we get a signal again. We get this one signal again. And, the one signal is just transposed here. It's, it passes through here, and it enables this wire again. And this wire, it allows the signal to pass. Right now, I don't have a particular shape running through the machine, but if we did, then at this point in time, the signal would be allowed to continue. So that's how the first phase of the ADJ works. That's the way it interrupts and resets the cycler module, so that in case of some tilt or some jank or whatever you want to call it, the machine gets a second shot at it, because I reset everything and let the machine try again. And that is the point in time where we get to the second phase of the timer. So I removed this belt piece right here, but usually it's like this. And now you see, the creeping kind of movement that we had before. Now we're going to get it on the second timer. And it's going to do the same thing. It's going to travel through all of this wiring, make the U-turn around the bend, come all the way back. And this is the point in time, the end of the line. Here, this is where it's going to indicate a fail. So the first thing it's going to do, very similarly to how this works, is it's going to trigger free flow movement for all of this, for this bottom piece of the ADJ as well. So that's the first thing it's going to do. But the second thing it's going to do, and now let's have a look, it's going to trigger, instead of a purple color, it's going to trigger a red color on the display. And the red color on the display, that is going to be responsible for shutting the machine down indefinitely. So as soon as these shapes hit this belt reader right here, let's see, because I don't recall by heart, I'm very sorry about that, how exactly I triggered that. So let's have a look at that together. Is it here? Here we have the purple signal that moves up to the displays. Yeah, I forgot how I did that, to be honest. Let me have a quick look. Apologies. Yeah, okay, so I had to run a test shape just to make absolutely sure. The thing is that I built this ADJ a long time ago, and it turns out that the way I set it up is it doesn't actually shut down the machine. So in the background, the machine is actually still trying all kinds of stuff. The algorithm has started over, and the only thing I did was, put this red triangle onto the display, which, when you look at it, if you observe the machine, there is no real, you don't notice the difference, but actually in the background, it turns out the machine was still, the machine is still trying all kinds of stuff. I thought I had built in something that would actually shut the machine down. It wouldn't be a lot of work to do, but it just turns out that I didn't, okay? So if the machine finds or doesn't find a solution after the time it takes for these shapes to run through the entire anti-jank device, then, as you can see, a red triangle will be output on the display. And that is how it works. So, as I said, the ADJ is not really an addition to the machine. It doesn't provide any useful contribution anymore to the machine, but nonetheless, I hope you had fun looking at the setups. There are some interesting setups, I believe, like, the various kinds of delay modules, the way that the signals get, the constant signal loops are created, stuff like that. So I hope you agree. I hope you had fun watching. We are almost nearing the end of our journey, but I hope you're still having fun, and I hope to see you again next video. Thank you for watching. Take care. Have a nice day. Bye-bye.